Um, okay. I can go back to my first slide, maybe. Okay, I will start. I am Marcos Sanzarena from the ICRR of the University of Tokyo, but I'm Mexican, so I'm happy to be here in my country. I will talk about a new experiment. It's called ALPACA. And first, I describe who is the ALPACA collaboration, then what is and how we work. So the ALPACA collaboration is a collaboration between three countries, Japan, Bolivia, and Mexico. We are around 50 members and 24 institutions. Uh, like this. Okay. So the name of our experiment is Andes Large Area Particle Detector for Cosmic Ray Physics and Astronomy. That's ALPACA. And just to show these animals, maybe not everybody knows, these so-called alpacas. And they live in Los Andes, Bolivia, and Southern America. They are very strong animals because they can survive at very high altitude. It's difficult conditions for living. So we are named after these beautiful animals. So as my colleague from Tibet, Kawata-san, explained, we are interested in gamma ray astronomy and sub-PeV gamma ray astronomy. We are interested in this because we think that observing these types of gamma rays, we can get the origins of the cosmic rays. So gamma rays in this energy range are produced by um, uh, cosmic ray interacting in the interstellar medium. So this is very new field. In the recent years, Tibet experiment observed Crab Nebula in this energy range, also Hawk and Lasso. And we have also the first detection of diffuse gamma rays, and Lasso has made a huge contribution with several PV sources. So it's a very interesting topic, but currently all our observations are in the Northern Hemisphere. So we want to start observations in the Southern Hemisphere, and this is the origin of our experiment. Okay, so Professor Takita mentions that air shower experiment is like going to hardware store, and so you go to hardware store and buy one product you have, and you have many products available. So this experiment has many results that we can explore, and these are some examples. For example, we know that from the Tibet observation of the cosmic ray anisotropy, there is a change when we increase in energy, and this fits with some results by the ice cube. So we would like to also obtain these results using ALPACA. Also, we can study the sun using the sun shadow of the cosmic rays. And interestingly, Tibet collaboration has shown that this shadow is affected by solar activity. So we can also study interplanetary medium using this kind of technique. So where is ALPACA? Is in Bolivia. And why in Bolivia? Well, it's an excellent place for this kind of experiment. We have a high altitude observatory, a large flat surface area. We have a great opportunity to observe the galactic center. And also there is a collaboration between Bolivia and Japan for almost 50 years or more. So it's excellent place. This is a picture of Bolivia, and if you can see here is our detector. We take this picture from the top of Chocaltaya mountain. So I'm going to explain a little bit the technique. I've been explained it before. So briefly, we use these scintillator units that are installed in metal box, and it has lead plates on top to increase the detection efficiency of gamma rays. And we have coverage. In this case, I'm only considering the prototype array, which we call ALPACA, as a small alpaca. And in this array, we have 1970 detectors, and we cover this area. And with this surface detector, we can reconstruct the basic characteristics of the air shower, so we can get the primary energy reconstruction using the density of the surface detectors. And we can reconstruct the incoming direction of the events using the timing information. So we can achieve a good angular resolution in this energy range. This study was made by Monte Carlo simulation with the prototype, which is called ALPACA. So this is not for the full array. So our experiment is hybrid to obtain the gamma ray with good purity. We use also underground muon detectors, and these detectors are installed 2 meters below the ground, and we have pools with 4 50 20-inch photomultipliers, and in total we have 16 in this 16 cells in this underground pools. And the idea, as same as the Tibet experiment, is to let muon component penetrate and generate signal underground. Meanwhile, the electromagnetic component is absorbed, mostly it's absorbed in the soil. So we can separate gamma ray showers from hadronic showers. So with this type of detector, our technique is based on gamma rays have produced very little number of muons. You can see here. Meanwhile, the cosmic rays are producing a large number of muons. So if we make a selection criteria, simple selection criteria, we can separate between the two groups and obtain good sensitivity. So this is a study of sources in the Southern Hemisphere. So this is the sensitivity of ALPACA for 1 year of observation and considering 5 sigma detection or 10 events in the the background zero range. So for the case of ALPACA, which is the detector that we now have in 1 year of observation, we expect to observe 4 sources with in the above 100 TeV. So, but this is using the underground muon detector. So the current status of our detector is like this, and I'm going to show what is the next plans. So ALPACA is currently this configuration, is now working, and we are going to show some data of this. And by the end of the year, we want to have this configuration. We need to build the underground muon detector, and we will expand the surface array. And for the next year, we plan to have the full array completed. So the next year, we will start observation with the full ALPACA array. So I'm going to show how we construct ALPACA. We start this work in June 2022 after the COVID pandemic. So uh, we lay out the scintillators, the 97 scintillators, and we put the cabling of the detectors in this special case to cover for rain and to protect the cables of all the detectors. So it was very hard work. Uh, we also install electric field monitors and weather monitors, as other mentioned in similar experiments. There is interesting topics relating to the weather and electrical storms. So we have these devices to make similar studies in this case. This is a picture of the full detector install, ALPACA. So we are working to the next stage. So this is a summary of what we have done so far. So we install all PMTs and calibrated. For this process, we put a smaller version of the detectors and we record muons and we do this for every detector and we set the gain very precisely for each detector. So after that, what we get is air showers, any 4 detectors that make a hit and have a signal larger than 0.6 particles within 600 nanoseconds. We record these events and we have this trigger rate, and our mode energy is about 7 tele-electron volts. So we start the full operation of the array in April 2023. The progress of the MD pool is as follows. We have been working in the optimization of the MD design. It's a very big structure, so we need to be study careful how we're going to build this building and especially to guarantee safe operation, because after putting again the soil on top of the detector, we still need to be able to work below in the detector, so we need to guarantee safety. So, but we now have a good design of this, and we are currently on the process of constructing these detectors. And the next topic is how are we going to fill the detector, and we study several possibilities, and the best option right now is to use water from a dam that is near, and we have tested the transparency of the water, and we find it using a simple water filter, we can use this water for our purpose. So this is examples of our data. So we show this data in the ICRC, the last ICRC. And these are events, reconstructed events that have energy larger than 100 TeV, but this is cosmic ray events. So we don't have yet how to separate. So next is the study of the angular resolution of the detector. We use a very clever technique, but simple. We use the even-odd method, in which we divide our array into independent arrays, and we compare each event, the direction of the 2 arrays. And with this, we find that we make this kind of histogram. The angular resolution is approximately half the median value of this even-odd method. So this is one way to determine the angular resolution with the data. But better or a little bit more complex method is the moon shadow. So we have studied the angular resolution of the detector with the moon shadow, and as you know, the moon casts a shadow over the Earth, and so it blocks the cosmic rays coming to our observatory. So with these 8 months of data, 220 days, we follow the trajectory of the moon over the sky, and we make this kind of maps and register which is the deficit in the number of events. So after making this analysis, we found that this circle is the size of the moon as it should be, and we obtained this moon shadow, uh, which is deflected because the Earth magnetic field. So we found a shift westward of 2.2 degrees, and we know uh, this is the expected value. We have studied this with Monte Carlo simulation, and we confirm, as I showed previously in the previous slides, we have a zero 0.9 resolution of our data. So this means that we have a good quality of our data, and we are ready to start other observations. We are hoping we can have the muon underground muon detector very soon. This is I'm forgetting about this. Right now we are trying to push a bigger array. So we hope to have ALPACA completed by the next year. So beyond this detector, we want to pursue mega ALPACA. So mega ALPACA will help us to know where is the highest energy accelerator in our galaxy. And for this, we will require a 1 square kilometer array and a lot of muon, underground muon detectors. So in this diagram, you can see the size of the ALPACA, which will be completed next year. And the next detector we want to build to extend ALPACA is mega ALPACA. So this is one idea we are pursuing, and it was reported in the ICRC rapporteur talk. So this is the sensitivity. We have made a basic study of the sensitivity of these instruments, and here comparing the observations with 1 year of ALPACA and the observations with 1 year of mega ALPACA and 10 years. You can see that we can observe a lot of sources in the Southern Hemisphere. Oh, this should be my conclusion, but it's here it is. Okay, so this is a summary of my talk. The Southern sub-PV gamma ray sky is yet to be explored, so we want to start ALPACA experiment to make this observation. Right now, ALPACA is under construction in Bolivia. We have calibrated and installed all detectors, and we successfully detect the moon shadow with ALPACITA, which is the prototype of ALPACA. And we have a confirmation of this moon shadow of 8.0 sigma. The angular resolution of our detector is 0.9 degrees. We will start the construction of this. We will start and finish, sorry. The construction of one empty pool by the end of the year, we have this. We hope to have this. And the next year, we are going to work really hard to complete the installation of the full array. So in very soon we start the observations of sub-PV gamma rays in the Southern Hemisphere. That's all.
Thanks a lot. So thanks a lot. Just to give me a scale, how does it compare in size to Hawk if you have ALPACA?
Well,
just roughly, is it same size or bigger? Or?
I think roughly is ALPACA is a little bit larger, but Hawk compensates that because water Cherenkov is had good sensitivity for secondary gamma.
Yeah. Okay, so are there other questions, comments? Let me see. Are there? Yeah, Karl-Heinz?
Yeah, perhaps a related question to Ralph's. So very nice progress. So my question is about the SWGO. How does it compare to that? We will have a talk later today about that. And,
yeah. So, in the case of only ALPACA, SWGO is larger, maybe 1.5 square kilometers. Maybe that's the that I have. But if we construct a mega ALPACA, maybe we can have a similar performance.
Okay.
Yeah.
Thanks for the nice talk. You mentioned that you have installed electric field monitors.
Yes.
Do you have any event to show?
Right now, I don't have data about this, but
you have recorded.
Yeah.
Okay.
Yeah.
Thank you. And we have one question in Zoom.
Yeah. So I don't know who is it. Please go ahead. Yeah.
Hello, Professor.
Yes.
We have many experiments using scintillator detectors and photomultiplier tubes. Is there are any new detectors, new developed so far, or any R&D is going on to develop new detectors to replace scintillators and photomultiplier tubes in gamma ray astronomy?
This is, please repeat the question. I think it's a very good question, but I'm not sure if I get the question.
We have so many experiments we are using since many decades, scintillators and photomultiplier tubes as a detectors in the experiments. Is there any new technology or R&D is going on to develop new detectors to replace scintillators and photomultiplier tubes?
Yes, for example, scintillators and photomultipliers are very good technology because the price. But I know there is many efforts to develop other types of detectors. So one good type of detector is a water Cherenkov detector because it's also low cost and it has good sensitivity to secondary gamma rays. So, and there is a lot of research about the shape of the water Cherenkov detector. So that is one example. I know that is a lot of research and development in this area.
And second question, many places experiments going on, similar methods. Why can't the international scientific community plan one experiment, bigger experiment, and make a wonderful experiment to observe all the phenomena? Is it not possible?
I think it's a good question, but maybe I'm not the person to answer this question. Maybe somebody else.
Okay, yeah. Let me see. Are there other questions here in the room? So let me ask, are you able to recycle or reuse Tibet RS gamma scintillators, for example, to save some money?
Yeah, some of the detectors come from the Tibet.
Okay, they come already. Okay, so you did already. Okay, good. Because
it's thank you, Professor.
Yeah. Thank you.
Okay, then thanks a lot for this very nice talk, and thank all the speakers in the